What is up, you guys? Welcome to the first lecture of this course on signal processing. This course is going to be a really big course. We're going to dedicate a lot of time for this course. And in this lecture, we're going to talk about signals and systems, different types of signals, whether they depend on time or space, or even highly complicated signals such as audio, images, and electrocardiogram EEG signals. We're also going to visualize different signals on MATLAB. Now, we're not going to master MATLAB in this lecture. I'm going to be frank with you. We're going to pick up on MATLAB on the go. So while I explain different topics and point out to different signals and operations, I'm going to pick up MATLAB and show you how the job could be done. Also, in this course, we're going to touch upon systems. So what is a system? Different types of systems such as linear, nonlinear, and operations that could be done using systems. So without further ado, let's get started. Okay, let's start by talking about a signal. So what is a signal, right? Since we're studying signal processing, then it only seems natural to define what a signal is. So a signal is actually defined as any physical quantity that varies with time, space, or even any other known or unknown variable, right? Mathematically speaking, we can describe a signal as a function as one or more independent variables. For example, say I've got a signal as S1 of t, that is, say, 5t squared plus 2t plus 7, right? This is one signal, right? You can also have another signal that depends on time as 2 of t, that is only 1, right? A constant. And you can have a signal, let's say S3 of t, that is cosine of t. As simple as that, okay? So if I were to show you how all these signals look like, let's say using MATLAB, then it would probably look something like this. So again, this is an introduction. No MATLAB skills are required. But, we'll catch up on MATLAB along the way. So if we have any doubts or questions or figures we'd like to plot, right? Okay, so we've got S1 of t over here. Let me define a time axis just for starting. That goes from 0 to 1, and let's pick 100 points. S1 is, let's type that down. There you go. S2 is 1, but we want it to be size compatible with t, that is, it should have the same size of t. And S3 is cosine t. Now let's go ahead and plot each and every one of those. So this is my S1. It looks something like this. Actually, let's plot them all on one figure. So S2 and S3. There you go. And S1 is really high. Actually, let's change this 7. Actually, you know what? Let's remove all this because this is lifting the guy up. I'll go back here and I'll do this. Then I'll plot all together. Actually, this S1 is really annoying. You see this signal? This signal is dominating the others, right? So for that, let me change S1 to 0.05 and then do the plotting again. There you go. So we just scaled S1 downwards, right? For a legend, I'm going to discriminate between the signals and do this, right? And let's label the axis, X label, Y label. Here, let's label the Y as amplitude. And there you go. So here we've got 3 signals, as you can see. Each one varies differently with respect to the time axis, right? For example, you can define other types of complicated signals, right? That could be functions of 2 independent variables. So for example, we can define a signal S that is a function of X and Y that takes on the following form. So let's say 3x plus 5xy plus 7y squared, for example. So if we were to go back to MATLAB, let me close this figure, and plot a 2D plot that plots s of x and y. Well, let's define my x and y variables to be on a mesh grid from 0 to 1, each one of those variables, and take s, that is 3x plus 5. You can see MATLAB is really easy to work with. It's just basically copy pasting what you have. And finally, I'd want to plot a surface s versus x and y. And there you go. This is how the signal looks like. Actually, x and y could go negative, so let's do that. So from -1 to 1, surf. Oh, we have to do s again, then surf again. And there you go. So this is a signal that doesn't depend on time, but depends on x and y, which are two spatial coordinates in a plane. Well, as you saw in both examples, whether we have signals that depend on time or that depend on space, right? We just express the signals as equations, right? As simple equations. However, there are cases where such a functional relationship is not known, or even too highly complicated to just write down on a paper, right? For example, speech signals. So speech signals are very nonlinear, and not just that, even more, they cannot be described functionally by expressions such as those you see in front of you. In general, a segment of a speech may be represented to a high degree of accuracy as a sum of several sinusoidal functions of different amplitudes and frequencies. That is, the following could be seen as an approximation of speech signals. So you can look at speech signals as an approximation of multiple sinusoids with varying amplitudes, so ai of t, varying frequencies, so fi of t, and varying phase shifts, so theta I of t. As you see, the amplitude of each of the sinusoids varies. So imagine how complicated it would be to express a speech signal that is an audio signal, right? Let me show you an example on MATLAB. So here I've got some code. No need to go into the details, but this is a speech signal and it sounds like this. Okay, so as you can see, this signal is very complicated to analyze or to write down on a piece of paper, right? It's too complicated. And what you see over here is just a mere approximation of this audio signal, right? Now, keep in mind that one way to interpret the information content or message conveyed by any short time segment of the speech signal is to measure the amplitudes, frequencies, and offsets or phases contained in the short time segment. So what goes on here is that we pick a short time segment, say this one, or maybe this one, right? And within this short time segment, we try to measure the varying amplitudes, frequencies, and offsets, okay? This is one way of, estimating or even trying to estimate and predict future amplitudes, phases, and frequencies. Another example of a natural signal is an electrocardiogram, or known as ECG. Such signals provides a doctor with information about the condition of the patient's heart. So to see how an ECG signal looks like, MATLAB has its MIT 200 dataset. So we load it. Let me close all and open a figure, right? So this is my figure. And let me plot ECG sig. So ECG sig. There you go. So what you see in front of you is the QRS complex peaks that are used in ECG analysis, right? So this is a beep, then a beep, and so on. So this is a signal, as you can see. We can approximate this as some mathematical equations. Actually, you see those peaks? This actually has a name in signal processing. It's called the Dirac delta function. So you could see several shifted. Well, that's the first thing that pops in my mind when I see such a signal. Sum of shifted Dirac functions, right? You have the ups and downs, of course. This could be machine noise or measuring noise, right? But what I see is spikes. There's where, or peaks, there's where the information is conveyed, right? Even though speech and electro ECG or even EEG signals are too complex to write down, right? Even though they're really complex to write down as such, they still evolve as functions as a single independent variable. An example of a signal that is a function of two independent variables is an image. So for example, if I close this figure and I open a figure, here's my figure, then let's say I load a certain image, right? So say my X, I'm going to read an image that is in MATLAB, the following. And as you can see, it returned a matrix. The matrix is of size 415 by 312. If I want to show this image, I'll pass imShow of X. As you can see, all I see is rubbish because I did something really dumb. That is, I did not import the color map, which is super important. So the color map should be imported with the image. Let's go ahead and show it. And there you go. So here's an image that is, back to what we were saying, a two-dimensional signal, right? That are the X and Y axes, right? They are also referred to as spatial coordinates because the signal varies. So with pixels, each point on the image is referred to as a pixel. And the pixel varies with spatial coordinates, right? As you can see here, we've got a red, whereas here we've got yellow, right? Where when you vary spatially, the color of the image will change. So the physical quantity that the signal bears is color over here, right? Now, we've been talking a lot about signals right now, right? We've been characterizing some signals that could be or not written down as functions of independent variables and other complicated signals such as audio, EEG, or even images that are more tough to write down, right? So you should always keep in mind that signals should always associate with signals the means by which these signals are generated. For example, speech signals are generated by forcing air through the vocal cords. So right now when I'm talking, actually exerting force through my vocal cords to speak and thus emit an audio signal. On the other hand, images, for example, the image that you see in front of you, are obtained by exposing a film to a scene or an object. Thus, signal generation is usually associated with a system that responds to a stimulus or force. In a speech signal, the system consists of vocal stuff such as vocal cords, vocal tract, which is also known as the vocal cavity. The stimulus, in combination with the system, is called a signal source, right? So this is where the signal is initiated. This is where the signal is emitted, right? So this is the signal source. So we have speech sources, such as my chords. We've got image sources and many other various types of signal sources. This brings us to something really important, which is a system. So in many universities, signal processing is usually also called signals and systems. Okay, so while studying signal processing, you should always keep in mind two ideas. You should always bear in mind those two ideas. What is a signal, and also what is a system? So a system may also be defined as a physical device, right, that performs an operation on a signal. For example, a filter used to reduce the noise and interference corrupting a desired information-bearing signal is called a system. So, say I've got a box here. In future lectures, we'll try to, unbox this, unbox this box to see how filtering is achieved, right? So again, I've got this filter, I've got a signal that is passed into this filter. Well, say that my signal is, corrupted with some noise. So instead of this nice looking smooth signal, I've got some noise around my signal, and I desire something like smooth. I don't want noisy stuff. I don't care about the noisy stuff, right? So my filter's job over here is to cut out noisy or maybe even interference signals that are, distorting my signal, right? So in this case, the filter performs some operations on the signal, which has the effect of reducing, or also referred to as filtering out, the noise and interference from the desired information-bearing signal. And just one thing over here, when we pass a signal through a system, as is the case of filtering, we say that we have processed the signal, right? In this case, the processing of the signal involves filtering the noise and interference from the desired signal. In general, the system is characterized by the type of operation that it performs on the signal. For example, if the operation is linear, the system, filter, or should be system, a filter is one type of system, right? So if the system performs linear operations, and we'll define what linear is in future lectures, then we say that the system is called a linear system, okay? On the other hand, if those operations are nonlinear, the system is said to be nonlinear, and so forth. So a system is named after the operations done on the signal. So if you're performing operations that are, bilinear, then your system is called a bilinear system. And usually those operations done are called, or are usually referred to as, signal processing. It's when you're performing or processing your signal through operations. Now, for our purposes, it is convenient to broaden the definition of a system to include not only physical devices, but also software realizations of operations on a signal. In digital processing of signals on a digital computer, the operations performed on a signal consists of a number of mathematical operations as specified by a software program. In this case, the program represents an implementation of the system in software. Now, as you will see in future lectures, we will be focusing more on digital signal processing. Since many of the signals encountered in practice are analog, we will also consider the problem of going from analog to digital and vice versa. But the primary focus of this course is on digital systems. And that's about it. So in this lecture, we introduced you to signal processing, what a signal is, types of signals, what a system is, how to classify systems based on its operations, and thus signal processing. So we process a signal through operations on that signal. Thanks for watching. If you found this lecture beneficial, please leave a like on the video, subscribe to the channel. If you have any questions whatsoever, kindly leave a comment down in the comment section below, and I'll make sure I'll get to it as soon as possible. Also, please consider donating to my Patreon account any amount you wish. Thanks for watching, and I'll see you in future lectures.